Hi folks, in this video I'm going to be running you through basically kind of start to finish on what to do with the end of year project. So here I have got a video of a cork disc that is rolling down an incline, and we're going to do a video analysis of this rolling motion down an inclined plane. Uploaded Logger Pro on my computer, and I'm going to go to the insert button and click on movie. And so I'm going to locate the movie that I just have. Now remember that you need to be making your own movie in this case. All right, so here's the movie I have. And I happen to know that this cork disc has a diameter of 16.5 centimeters. So let's pull up the video analysis toolbar up here on the right side. And we're going to set the scale. That's this button right over here, the yellow ruler. And we're going to measure the distance from right to this edge all the way over here to this edge, and we're going to set that to a distance of 0.165. Okay, all right, so now we have a scale set up, and the next thing is we're going to need to choose our coordinate system. So we click on the third button from the top right, and we can either put it maybe here, right at the very bottom, all right, or we could potentially do it at the middle of the mass and then maybe rotate the scale so that it's going along the direction that it's moving. So it's really up to you what you wish to do, all right? Up to you how you want to look at it. The first time I went through it, I actually did it this way because I wanted to find the acceleration just parallel along the plane, the inclined plane, and then I could find that the acceleration vertically would be 0, as we had normally solved problems that would be accelerating down an incline. But then I found in terms of coding, it would be a little bit easier if I actually just left it as normally vertically straight up and horizontally going to the right. So let's just do that for now, just to kind of show you what we can do. I gotta reset that so it looks like perfectly horizontal, all right, and then just reset it right to the middle. So the next thing we're going to do now is going to start to plot points. Now, just to point out, you might notice that when I run this video here, there's hopefully you have got the time set up. So some of you guys might have had a lot of lag time, and you might click on this button over here, which is the movie synchronization time. So let's suppose that you don't want to start right at time 0 on your movie time, and you move ahead a certain point, like just when he releases the stick here. So then you might choose to click on this movie synchronization time and change that graph time so that it's 0. Okay, you would place this to be 0, and so then 0 on the graph time would represent that movie time. Now, so if you have a bunch of lag that's happening on at the beginning of your movie, you haven't trimmed it, that you might want to do so that your graph time is going to be synced to when you first getting points. Okay, otherwise you're going to have points all shifted to the right in your time scale. All right, so in this case, actually, I think the movie is right up, it's pretty much starting at the beginning. So I'm going to use the very first point here, and I'm going to start to now plot points. So I use the point tool here, and I start to click on. I'm going to just plot the center of mass of this. So I just click here, and I keep clicking, and you can see there's data points that are being inserted into my table here, and then eventually the object starts to move here, and I start to move with it and start putting the points in the right spot. Okay, so I'm going to pause here for a second and just finish the job because it's going to be a lot of clicking here. A lot of clicking and actually kind of done very quickly, so it isn't the best line that I drew through here. But nevertheless, let me auto-arrange the screen. I'll press Command R, and you can see the data being plotted over here. Okay, now if I would like to, I'll just turn off the video analysis toolbar over here on the side. Maybe I can't. Anyway, let's go to the graph, and we're going to insert another graph in here. So we can see kind of two graphs at the same time. I'm going to do Command R because it's got hidden behind there. And you can see that there is a y velocity and then there's an x velocity. Let's actually show both of these things. So we have over here x and y, and I can see this kind of trend. So in between here, because at the beginning it's just being released, but in between here and here, we can see that it is roughly a linear fit. So we're going to fit a linear curve on both of these guys, and you can see that it is accelerating along the vertical direction with a negative slope, which is the acceleration of negative 0.0959 0.09496 meters per second squared, and the horizontal acceleration is given here to the right. So this is going to be helping me with my coding because it's going to tell me what my acceleration horizontally is and what my acceleration vertically is. Okay, the other thing that we need to consider too is that the object is rotating, and we're going to talk about that. So if I go back to this video and you look at it, you can see the blue dot and the red dot are rotating about here, and we need to consider that as well. But we'll take a look at that later. Let's start with just one piece and see if we could just make the ball translate downwards, and then we'll add the rotational bit in a minute. glowscript.org, and we're going to sign into our account, and we're going to, I'll just go into my jump folder here, and I'm just going to create a new program. All right, we'll just call it rolling .disk. Okay, so we can create our program in here and see what we're doing. I would probably write down for my coding is to basically have the initial conditions of what I've got for my video. So first of all, I happen to know that the radius is 0.165 divided by 2. That was the diameter. So this, just writing this down, this is the radius of the cork disc. Okay, second thing we're going to do is maybe put down the acceleration. So AX, now where is that? AX, if you recall from earlier, is over here. That is the acceleration. It is going to be along the x-axis, 0.3615. We can put it in there, and we also need to put in the vertical acceleration, which is going to be some negative value because it's falling vertically. So again, let's go back to our Logger Pro and look for that acceleration value. Along the y-axis is negative 0.09496. So let's go ahead and put that one into our glowscript program. I put in the acceleration along the y-axis now. All right, some other conditions that we might want to put in here. We might want to set time initially to be the setting time to be 0. And then we'll set the increment at, I don't know, 1/100. So this is the setting the time step or time increment. Okay, so next thing is let's start off just thinking about what we want to do. We want to probably set up, setting up the scene. All right, this is kind of thinking about what we have to do, which is, all right, and then we're going to probably need to make a ramp, and then we'll probably need to make a cylinder. All right. Oops. So let's start doing that, and then we'll just make, first of all, I guess maybe we can start just making a cylinder here. All right, we're going to make a cylinder, and I'm going to position at the origin with a radius r and a length 0.05, and it's going to be having, this part is particularly important, having the axes correct. So 0 for x and y, which means that you're going to be seeing the face of it, and then it's going to be going through the screen. Maybe if I can show you kind of what that would look like. So if I kind of tilt this on here, you can see that's my cylinder over here. Now it's occupying the whole screen, so maybe it would be a good idea to set up a scene in here. So I've now set these attributes for my scene in here, and so if I run the program here, you're going to see now it's kind of out, really focused on it, but at least has made the background white. So maybe what we need to do is make a ramp here. Okay, I've added a few things now in my code. I have the length of the ramp, which is 2, and the thickness here is 0.05, and I'm using a box for the ramp. So I'm positioned at the origin, and I've got it length and thickness, and it's going to stretch back 1. So if I run this, you'll see now that unfortunately the cylinder is in the middle of my ramp. So I need to shift that cylinder up a little bit here. How will I do that? Well, I need to change its position. So horizontally, maybe 0 is fine, but if we change this and make this maybe the thickness of the ramp, shift it up to thickness, do we put the cylinder in the right spot? Well, it moved it up a little bit, but it looks like it's still inside that field. So we need to maybe multiply that thickness by 2. See if that. So feel free to kind of muck around until you get it right, so it just looks like it's just sitting on top of it. Now the other thing I need to consider is that the ramp is tilted. And how are we going to tilt this ramp? So I'm going to use a function called rotate. And I'm going to need to rotate it some angle. Now I need to define that angle. And how would I figure that out? Well, I know that it is accelerating horizontally this value and vertically that value. So if you think of a little bit trick, if you know how much it accelerates horizontally and vertically, I could figure out the angle by defining it as, say, the arctan of AY divided by AX. So this is going to be the angle of incline, or actually decline, I guess, for the ramp. All right, so now if I run the program and I'm now rotating that ramp with an axis along the z-axis here, we'll see what happens here. So now I've got the ramp rotated, all right, and now we just need to make that ball, or that cylinder, sorry, roll down the ramp. All right, so we'll put the ball or the cylinder at the top of the ramp later on, but let's just try to make the cylinder rotate, or actually rotate, but actually translate. So we're going to now create a loop, and we're going to make the cylinder move down the ramp. That's the next bit that we're going to do now. So there might be some other initial conditions that we need to set. For example, we might want to indicate that the initial velocity is basically 0, right? So we're going to set that, setting initial speed. And you may not need to do this because in our equations you may just neglect that term. We also want to set the acceleration. So we're going to look at the acceleration as a vector quantity, and we want to use it both the AX that we define, AY, and we'll keep along the z-axis 0. So here we're setting the acceleration as a vector. Okay. So now let's make the loop rotate. Now how long do we want to do that for? So if we go back to Logger Pro for a moment, you can see that the time runs from 0 to roughly about 2.5 seconds. So we're going to need to run this simulation for about 2.5 seconds. Okay, so back to our glow script, and I'm going to use a while loop while t is less than 2.5. Okay, you'll notice that after I put that colon, it's going to automatically indent it. We want to slow down that animation, so we're going to slow it down by whatever the inverse of dt is. So 1 over dt, in this case would be 100. Next thing we want to do is we need to keep changing the position of our object. So in this case, our object is the cylinder, which I've just labeled for this point, capital A. So we're going to change its position, a.pos, and we're going to use the kinematics equation. You can think of it will be, x 0 plus v0 times t plus 0.5 times a times t times t. But we're going to try to do it in all 3 dimensions because we have an x, a y, and a z accelerations. So what we can remember, by the way, the initial position we could just assume is 0, so let's just get rid of that term. We don't need that. And the initial velocity, we do want to write that as a vector quantity. So you may want to say it's a vec, where it has 0, 0, 0, and that instead of just doing one quantity being 0. So we remember that we're looking at acceleration as a vector quantity, having x, y, and z components. We have to do that with velocity. All these terms have to have have basically 3 components to them. Then multiply by t, then multiply by acceleration times t. I think we're good. Now what we need to do after we are making it move, we need to increment time. So t equals t plus dt. All right, so I don't know. Let's see if this works out. All right, it's moving, it's rolling, and it's kind of going down the ramp, but it's not on top of the ramp, so I do need to adjust the position of it. So the art of debugging, because when I ran it here, I saw that I thought I had put the cylinder at the top, and now it suddenly went back into the middle of the ramp. And maybe sometimes we might want to add a little thing in here, like seeing wait for click. So that way what's going to happen is before I start running that loop, it's going to sit there and pause, And oh, look, I have it in the right spot, but then as soon as I click and it goes into the loop, it suddenly then moves into the field. So what caused that problem? Well, I suddenly realized that maybe by getting rid of that x0, I should have left that in there. So maybe I should put like an R initial position here. And really, or X, it doesn't matter. And we need to realize that, see, we assumed that it was 0, 0, but actually the cylinder was placed not at quite 0, 0. It was shifted vertically up a little bit here. So before we go into that loop, we need to basically set the position initially, we'll call R0 or X0, to be the A dot pos. So now it's going to always be referencing from the very initial position here. So if I run it, hopefully, it won't shift. If I press click, and now it's going to roll down that incline. Beautiful. Okay, so we got it rolling down the incline. So the next thing we need to do is make it roll. So let's take a look at that now. Okay, back to Logger Pro, I not only wanted to translate downwards, but I also wanted to roll. And you can see if as I play this video, I have both a blue dot and a red dot that are pivoting around that center point. So let's add those points into our program now. So now I've added these 2 points. I now also made the cylinder twice the radius it was before, just because I wanted to be a bit bigger, and I had to shift things up a little bit. So you'll see what little changes I've made, but let's just run the program so you can see it. That's what I'm trying to make here. I've got the 2 dots here. If I press play, oops, unfortunately these dots are staying where they are. So how do we fix it so that these dots are going to roll with the disk? And so that's another feature we need to learn about, is compounding several objects into one object. So I'm going to add a line of compound. This C stands for cylinder, and it's going to compound object A, P1, and P2, those points. And we're now going to set the new position to be capital C for the cylinder instead. So now if I run the program, hopefully I will see that it moves. Oops, what's going on? It doesn't seem to be moving. Some error I'm making. Oh, I see that I've changed the new object to C, but then in my loop in here, I've not changed this capital A to capital C, because that's the new object that I'm rotating. So if I run it now, hopefully everything will roll along here. So now if I run it here, but you can see that the object is not pivoting, it's not rolling as it goes down the incline. So I need these 2 dots to rotate as it goes down. So back to Logger Pro, we need to work with our video and get some information from this video, how fast this thing is accelerating down the incline. Because right now we're only looking at the center mass as it accelerates, but we want to also look at the angular acceleration as it goes down. So how are we going to do that? Well, there's a couple ways that one could do it. Maybe this might hopefully be the easier way to doing it, but there might be an easier way. Let's see how this works out. Now, I need to look at an outside point, either the red point or the blue point, and plot its movement as well. So we go back over here, and we're now going to add some more dots. Besides the middle dot, which is the center mass, we're going to click over here into the point series, and you're going to able to add more than one point series. So we add point series in here, and you'll see, notice that now I have a new set of point series that are coming up in here. We're going to call it X2 and Y2. Okay, so if I now choose to plot those points in here, I'm going to choose to do it for the blue dot. I will just click here, and keep clicking until I get the object starting to rotate. And you can see now I need to keep clicking and show its pattern. So I'm not going to bore you with me doing all this clicking, so let me go ahead and do that now. Okay, this again was done very quickly, but you can see as I roll it here, now I'm getting a plotted point. Looks like a cycloid, right? So that's, these orange dots represent the movement of the outside point as it rolls down. So we're going to need to use that information to figure out the angular velocity. So I'm going to go Command R here, and we're going to look at, well, what we need to do is use this outside point relative to the center and find out what its x and y on that little unit circle, that circle in here. And we're going to need to find out how far it is horizontally and how far it is vertically relative to the center. So let's imagine that you were to only observe just the center of this moving, and you wouldn't be seeing it translate to the right. So we need to do create some columns in here. So what we're going to do is we're going to go to your data, a new calculated column, and we're going to create a x relative to the center of mass. So this is x relative to center of mass. So we'll call that x, I don't know, subscript maybe 0, and the units will be in meters. And what we're going to do is we're going to subtract that outside point x2 from the inside point x. All right, and so we're going to be getting how much distance is always from the center here. And so we get that. Now, similarly, we're going to do the same thing for the y. And there I'm setting up the y one now, and I get that called. Now what we need to do is find the velocity along the x and velocity along the y for that particular point relative to the center. So we're going to create another column, new calculated column, which will be the x velocity relative to center of mass. Okay, so we'll call that v subscript, I guess, 0x. And the units will be in meters per second. And the expression we're going to be using is something called a derivative, which is basically taking the slope of the tangent line at that point. So under the calculus, you click on derivative, and then you just click on x relative to the center of mass. And that's going to get you the x velocity along the x-axis. And similarly, we're going to do it for the y now. All right, and this is my calculated column for the y velocity. And so the next thing we need to do, and we can change this graph so that now maybe we want to look at just the x and y velocities and see what that looks like. Let's get rid of the first one and second one and go now to the velocities in here and see what that looks like. And it looks like something like this. When this is high, that one's low, and when that's low, and so forth. So maybe a little bit complicated. What we need to do now is to find the resultant velocity v of this. All right, so we're going to need to create another data column in here, and we're just going to call that the resultant velocity. All right, v, and we'll just call that v sub 0 in meters per second. And so if you think of this as got an x and a y component, makes a nice right triangle. So we're going to be using square root, Pythagorean theorem. We're going to take variable x velocity. We're going to square that, and then we're going to add that to the y velocity, and we're going to square that, close that brackets, and now that's going to get me the resultant velocity of this. So now if I just actually plot instead the resultant velocity, I get a nice straight line. So in here it's increasing linearly along here, and I get a nice linear fit. That's how fast it's moving. But maybe that's not what we really want. We actually want the angular velocity. So let's add in one more column. Let's do a calculated column and call it the angular velocity. So the short name is going to be Greek letter omega, and this is going to be in radians per second. So to do that, if you remember your equations from rotational motion, the tangential velocity is equal to r times omega. So omega will be really the tangential velocity, or the resultant velocity on the outside, divided by our radius. And if you remember, our radius was 0.165 was the diameter, divided by 2. So our radius is half of that. So we create that, and maybe we don't want the resultant velocity, but we want the angular velocity instead. So let's do a slope of that, and do a linear fit, and that's the piece of information what we need. This wheel is rotating with an angular acceleration of 3.836 radians per second squared. So back to our code, we're going to add in alpha. All right. If you want to get fancy, you can look up the alpha symbol online. I quickly Googled it, copied it, and instead of writing the word alpha, I'm just actually going to use the property Greek letter here, alpha, and we're going to make it have a angular velocity of, what was that again? It was a value of 3.836. 3.836. Oops. 3.836. And this is the setting the angular acceleration in radians per second squared. Okay, so now what we need to do is we need to make this whole object rotate, right? So how are we going to do that? Well, there's a similar equation just like we have over here. We're going to need to rotate it angularly. How do we do that? Well, we need to define maybe the initial angle. So again, let's put the initial angle. Now that would be theta equals 0, right? Again, if you want to get fancy and use the Greek letter theta, you might be able to find that online. So I'm setting now the angle theta to be 0, and now we're going to use kind of similar equation. Theta equals theta naught plus omega naught times t plus a half times alpha times t times t. So this is going to now rotate it about a particular axis. All right, have we done everything right? Well, we're rotating it a certain theta. So now that's just changing the angle, so we have to actually cause it to physically rotate. So we're going to now take that object, which is our object is called C now, and we're going to rotate it about its axis. So we do C dot axes equals vec, and to rotate it, we're rotating, remember that we want to rotate it both x and y and keep the z the same thing. So you're going to need to use cosine and then whatever your angle is. So your angle is theta here, right? And then we also have, that's the x component, the y component would be sine of that angle, and z will be just 0. Okay, I think I'm good, but maybe I need to double check that I've defined all these variables. I haven't really defined theta initial, so we probably want to make that defined in there, make that 0. What else have we not defined? The initial angular velocity, we're going to set that. So the initial angular velocity is going to be set at 0. Okay, and let's run it and see what happens. So as I run it here, ooh, I made a silly mistake. And you know what? It's funny, I did the same mistake what I did before. It's rotating the opposite direction. So that's a very quick, easy fix. We need to make it accelerate in the negative direction. So just change that to a negative 3.836. Let's run that program. Let's see if we can make it roll down the ramp. And voila, that's it. All right, this is already a long video, so I'm going to stop at this point because there's a few other things that you could do, like graphing the data, and also maybe you want to shift that cylinder so it's at the top of the ramp. But at least this gets you a start on what you need to do in your project and how to make things rotate and also translate and how to use that information that you got from Logger Pro. All right, hope this helps.